Okay, here. So for question number 4, it asks us to explain how the eye focuses light. So here I've drawn a sagittal cross-section of the eye. I'll go ahead and label a few things here. So here we have the cornea. Here is the lens. So if we go ahead and say that this right here is the point that we're looking at, there's going to be light that is reflected off of that point to our eye, kind of like this. It's going to be spread out in this way. And so what happens is the light will be bent 2 different ways. Firstly, by the cornea, like this. It kind of becomes flat in this way. And then from the lens, we'll also bend the light down here to the back of the eye. And here in the back of the eye, it is lined with photoreceptors, which are what capture the light that is bent by, here we have our object, and the light is being bent here at the cornea and then at the lens to converge at the photoreceptors. And so now I'm going to talk about some variances that happen in the eye in terms of bending light. So I'll go ahead and just do a quick little drawing here. Say we have our object here, and the light gets bent first by the cornea and then again by the lens. But instead of converging at the back of the eye where the photoreceptors are, it will be back here behind the eye. So at this point where the photoreceptors are, things will seem blurry. And so this is specifically for things that are close up, and this is called hyperopia. And this is less common in terms of impaired vision, but this can happen in younger people who can grow out of it when their eye increases in size to reach that point where the light converges together. So that is one example. Go ahead and erase this and talk about a different example. Say this is an example of someone with a larger eye, and here the lens will converge the light to this point. It will be a little bit short. This is called myopia, and this person will be okay to see things close up, but will struggle to see things from far away. So here I've highlighted and colored a few different parts of the eye that I'll talk more specifically about. In red, we have the ciliary body, the muscles of the eye, and in blue we have the suspensory ligaments that hold the lens of the eye and control the lens of the eye. So from the side here, we have 2 different options, basically, of how the lens will look. So also drawing from this sagittary plane, the lens can look like this, nice and round, and this will be for seeing up close because it will bend the light more and allow us to see things that are closer up. So I'll go ahead and draw what that looks like, looking straight on the eye. So what that will look like is, here we have the ciliary muscles, and these are going to be closed. They'll be tight and contracted. And that will cause these suspensory ligaments. First here, I'll draw this lens. It will be round and bending lots of light, and that means that these ligaments will be nice and loose. They don't have a lot of pressure on them because that muscle is squeezing in and relieving the pressure on those ligaments. So we have the muscle, the ciliary body that is squeezing tight, which makes these filaments loose, and this lens is more of a round shape like this. It's able to bend light more and see up close. Conversely to that, we have the flat lens, which is the thing that helps us to see far away, and it bends light much less. So from the same sagittal plane, this lens is going to look a lot more like this. It's going to be flat like that, and it's not going to be able to bend light as much. So I'll say I'll go ahead and draw the lens in here, and what happens is this ciliary body is going to be loose. It's going to spread out. It won't be contracted. And that means that these filaments, these suspensory filaments, are going to be pulled nice and tight. And so that pulling on those ligaments is going to flatten this lens just like this. And that will allow us to bend light less as it travels into our eye, and that will help us to focus on things that are further away. So the human eye is able to recognize light that is in the visible spectrum of the electromagnetic spectrum. And this light can be described as photons, and their energy is based on their wavelength. And so the visible light spectrum is about 380 nanometers all the way to about 700 nanometers. And these are the colors of the rainbow that we are able to see. Okay, so now I'm going to quickly describe the two different types of photoreceptors that we have in the retinas of our eyes. So first, I'll go ahead and just draw a little picture here that kind of is brief, somewhat related to their shape. These are called rods, and these are called cones based on their shape. So with rods, we have about 120 million of them in our eyes, where cones we have about 6 million. Rods help us to see black and white and help us to see at night, where cones help us to see all the different colors, and they help also with the sharp vision, being able to see clearly in high definition. Okay, so now I'm going to talk a little bit about how light energy is converted into electrical energy. So I've kind of drawn a little bit of an outline here, and I'll label it. Here we have the back of the eye. These are the photoreceptors. So these will be rods and cones, and that's kind of what I've drawn here. Here we have bipolar cells and ganglia cells, which will send signals to the brain. So this is the layout of the back of the eye with the photoreceptors. So what I'm going to do is I'm going to draw things in this orange color to kind of show what happens when light hits these photoreceptors. So here, first we'll start here with this G protein. Attached to this G protein is a compound that looks a little bit like this. This compound here is called 11-cis retinol. And what happens is when light hits these photoreceptors, this compound changes to this conformation and becomes 11-trans retinol. So when this conformation happens and 11-trans retinol becomes activated in this G protein, this alpha subunit will come over and attach to PDE. And so this activated PDE will come over here and it will interact with the cyclic GMP. So normally this cyclic GMP is what keeps this sodium channel open when it's dark out. But with the light, we're going to cancel out this cGMP, and that will ultimately close this channel so we won't have sodium flowing in. And as well, with this, by the same effect, we will have this voltage gated calcium channel closed, and that will stop the positive ions from coming into the cell. So here, these vesicles that have this neurotransmitter will not be able to send it over to the bipolar cell. And so the receptor on the bipolar cell is mGluR6, which when it's dark, this neurotransmitter will bind to this mGluR6, which will close this voltage-gated calcium channel called TRPM1. But because it's light out, we don't have any neurotransmitter going to this mGluR6. So this voltage-gated calcium channel is actually going to be open. And so we will have positive ions coming into the cell like this because of the light. And so they will continue down this pathway, and this neurotransmitter, these vesicles, will release glutamate here into the in between the bipolar cells and the ganglia cells. And this glutamate will bind to this AMPA, which will open up this channel and allow for more positive ions to come in, continuing sphere of influence. And here we have a voltage-gated sodium channel, which we know ultimately is what determines threshold. And so as this threshold is reached, we will go ahead and send an action potential to the brain. Okay, so now to talk about visual fields, we have to talk about surrounds and center cells. So here we have the photoreceptors here, here, and here. And these are horizontal cells. And here we have bipolar. And here we have ganglia. So what happens, say the surround cells are in the dark, they will release glutamate here, which will bind to the horizontal cells, and the horizontal cells will release a neurotransmitter called GABA that binds to the center cell that further inhibits the release of glutamate. So we know that less glutamate is what happens when there is more light. So when there's more glutamate, that's what happens when it's dark. So this GABA will help inhibit the release of glutamate from this center cell. And so the less glutamate that goes to the bipolar cell will mean that there is more light on the center cell, which will help begin this action potential that will go from the bipolar cell to the ganglia and to the brain. So these horizontal cells, when activated by glutamate, will further help the inhibition of glutamate on the on center cell by releasing GABA. So now to explain how that takes a role when talking about action potentials sent to the brain specifically, I'll go ahead and start by doing a little representation. This we will call on center, off surround. And so if light comes in and is hitting all of these places here, we know that the surrounds are off, so the light will not cause them to create action potentials. But because the center is on, we know that those action potentials are going to happen. So basically we can give these arbitrary numbers. We can say that the surround makes up for about 40% of the total capacity and 60% of total capacity for action potentials. So if we have light hitting this entire field, and we have an on center that's being hit by light, then we know that 60% of these action potentials are going to fire and go to the brain, and these 40 on the off surround are not. So we'll say that this is the 60%, or we can even say 6 out of 10. So we'll go the other way here, and we'll say this is on surround, off center, because we know that they always need to oppose each other. They can't both be on or both be off. And say we have light hitting all these places here. With these given ratios, these arbitrary numbers, what we can tell is that this light is hitting the on surround. So we know that we have 40% of those action potentials being sent to the brain, or 4 out of 10. And so these are marked by these little graphs that kind of show the amount of action potentials. And so each one of these will represent how many action potentials are being sent to the brain based on if we have an on center or off center, and depending on where the light is hitting. Because there are situations where we can have light that only hits a little bit of the field, or it hits most of the field but not all of it, and that will change our ratio here. So say for this example, if we cut out this section, then we have our 60% here of our on center is still going to be activated because of that light. But we also have no light coming to this 20% here from this surround. There's no light here, and because it's off, it will also contribute its 20% of action potential. So we will have an 80% here. So there are different ratios that can happen based on how much light is hitting each field and where it is hitting. But we can kind of calculate that with arbitrary numbers of the center accounts for 60% and each surround accounts for 20% of the total amount of action potentials that can be sent off to the brain.